everyone, our plasma class begins. What we will study in this class? Non-thermal plasma sources, radio frequency and DVD devices. So RF stands for radio frequency. In the previous class, what we have learned in the APPJ, there basically operates say in the regime of some kilohertz, okay, maybe say 10 kilohertz to say 100 200 kilohertz kind of thing. But here you know that the device that I will be explaining in this class is operating with the standard industrial frequency 13.56 megahertz. So the operating regime is quite different in this radio frequency devices, and I will be discussing about the dielectric barrier discharge devices. So they are DVD. Unlike in the previous case where you have learned about direct discharge between two electrodes, here between two electrodes there will be dielectric media, and then you will be applying the field, and that will cause the your breakdown to happen and discharge will take place. So we start with the radio frequency plasma device. So a typical configuration of 13.56 megahertz radio frequency atmospheric pressure plasma jet. So they are also APPJ, but they are in megahertz APPJ. So what you are seeing on the upper right corner, this is photograph of an actual RF cold plasma device and a tiny jet that you are seeing coming out from here, and this is basically the APPJ torch, and this is the nozzle and nozzle cap here, where basically the discharge forms. As I told you that it breaks down the shortest gap in the structure, whatever the structure is there consisting of the central electrode and the outer electrode, it will break over there. This is also a direct discharge between two electrodes. So there is a central electrode and an outer electrode. So the schematic that has been shown over here, it explains the structure of such devices. What you are seeing, this is the central electrode, and there is a nozzle cap, this black one, and this is the outer body, and there is a spacer which maintains a gap between the central electrode and the outer electrode. Both are metallic. So in this device sometimes the electrodes are chosen as aluminum, so that also works fine over there. Now what you are seeing here, there are mass flow controllers here. So they are mixing with argon the main plasma gas, some part of nitrogen and some concentration of oxygen. So they are mixing that, and then there is a mixture which uniformly mixes all the gases that you are interested in, and they enter into the plasma device, which is called plasma torch. So this is your APPJ plasma torch. Now what else are required? Because of a specific operating regime, this 13.56 megahertz, you actually need to cool the body of the torch so that the temperatures remain within the bearable limit. So these walls are double walled so that it can be cooled using flowing cold water, and there is an RF source. So here, as we have fixed the frequency as 13.56 megahertz, and these devices usually can operate at bit higher power. So here the device is having a power of 1 kilowatt compared to these ARC devices which operates at tens of kilowatts. It is quite less, and this power supplies are very portable. So as you can see that it is just plugged in this slot in this device, and this is a trolley mount system, a small trolley mount system on which this torch is mounted, and the power supply is included in that. This RF power supply requires a matching network so that it can impart the maximum power into the plasma. So that part is usually a automatic matching network, and that couples the power of the RF with the device. And the plasma jet that is basically forming in this zone, that comes out from the nozzle like this. So this is the plasma jet. Okay. Now the plasma jet that comes out from there, uh, I was talking about the radicals that is generated. If you are using pure argon, then what we can expect? We can expect the radiation that is very characteristic of argon. So we will get the characteristic line spectra of argon. So this is what is expected. And in the range of 700 to say 850 nanometer or 900 nanometer, you see the kind of lines that are coming out from argon plasma. So these lines are already listed in literature, so you can just go there and find out which of the lines correspond to what. So we have identified all the lines 1 to 16 that is present in this spectral zone as the lines from pure argon. But from what actually? Argon atom or argon ion. So although it is a plasma, the degree of ionization is very less. As I told you, the electron density or ion density will be of the order of 10^20 or so, very close to that. But the neutral atom density is how much? This is at atmospheric pressure, so it will be around say 10^24, 10^25 kind of order. So basically, what you are exciting the atoms, and the line spectra what you are getting here, it is from the argon atom. Now, when you are discharging the argon in air, what you are seeing, that is very interesting. You see here that you are seeing all the lines which are present in argon, see 1, 2, 3, 4, 5, like you see corresponding all lines you are getting over here. But in addition to these lines, what you are seeing over here, that you are seeing a oxygen an oxygen atom line, atomic lines of the oxygen. You see here this zone and this zone, you are getting a signature, although small, that signifies that this jet, whatever you have generated using this plasma, this atmospheric pressure plasma jet, is able to break some of the oxygen atoms, or rather oxygen molecules, which are present in the atmosphere. And breaking them, what they are doing? They are breaking them apart and forming the oxygen atoms, nascent oxygen atoms, which are excited in the plasma region, and they are emitting their characteristic line, and which are getting recorded in our spectrometer. So here these are the oxygen atom lines, and that is very interesting, because a reaction which occurs with oxygen molecule, that will occur much faster when you are using nascent oxygen atoms instead of molecule. So the same reaction may be further faster if you are using ions of the same molecule. So this is a known fact. So whenever you are giving this nascent oxygen, the oxidizing ability for a particular reaction, whether it is a biomedical application, or it is plasma polymerization or functionalization, you can use this property very efficiently. So one important thing, that you are not introducing any additional oxygen into your plasma jet initially. You are pushing pure argon. But when the jet is impinging in the air, it is able to generate nascent oxygen species by breaking the oxygen molecule. So that is very interesting, that you don't need to get an oxygen cylinder, you just discharge the plasma in air and you will be able to generate the oxygen atoms. And these atoms can participate in the desired uh, chemistry what you are looking for. So in tutorial, actually what we'll do, we'll give you more details on how the species are getting generated and how these species can be used for functionalization purpose and many important applications which can be done only because these kind of properties are readily available with this kind of jet. So not only that, your this oxygen species in tutorial will be seeing that instead of pure argon, when you are pushing oxygen, you get similar lines, much stronger lines at the same location as we are seeing over here. So we skip these details and we will discuss those in our tutorial in a much better way. So, this is with nitrogen instead of oxygen if you push there. So there are certain other very interesting things which we will be discussing in our tutorials. You can see the spectra is quite changed compared to the one that you have seen over there. So this is one which we would like to draw your attention, that in this radio frequency plasma device, as you are moving away from the nozzle exit to the downstream, okay, so how much you have moved? You have moved by some 5 mm, and this is the electron temperature. You are seeing that as you are moving down, this electron temperature measured spectroscopically is dropping very, very fast. You see here. So here it is around 30,000. So it is around 3 eV kind of thing, close to that. And from there it is coming down here. You are seeing it is around say some 8,000 degree Kelvin. So nearly 1 eV, less than that. So this is when you are pushing some 30 liter per minute of argon and 0.2 liter per minute of nitrogen. This SLPM stand for standard liter per minute. Standard liter per minute. This is why, because liter has no meaning unless and until you tell specifically the temperature and pressure. Okay. So if you are suppose 1 liter of argon, if you are increasing the temperature, that can be 2 liter, 3 liter, whatever, if you are keeping the pressure of course constant. And then if you are having some gas of some volume, if you are squeezing it, increasing the pressure, this volume changes. So SLPM has no meaning unless and until you tell that LPM, liter per minute, unless and until you mention the kind of pressure and temperature. So standard means you are pushing that at standard temperature and pressure. So that is the marking in that flow meter. So when you are telling that, so it is corresponding to that value. So you are specifying very precisely. Now here on the right side, what you are seeing here, while the electron temperature is so high, you see that 30,000, and here on the right side, what you are seeing with distance, the temperature of the gas. You see that at the nozzle exit, the temperature is pretty high, but not that high. You can even touch it by hand, but it is high. You cannot keep your finger there for a long time. It will be burned, or you will feel the heat actually intensely. Now, as you come downstream, so it is 4 mm, then 6 mm, 8 mm, it is falling, and when you are around 15 mm, that is 1.5 centimeter, this is a small distance, then what you are seeing, the temperature is around 40 degrees centigrade. This is the zone where you can use this plasma for direct application. So earlier, when you were using kilohertz plasma, we are referring to the temperature nearly the nozzle exit. As you go downstream, you can reach any temperature, but at the same time, the radical density drops. But they are there, but the concentration comes down. So you need to make a delicate balance between the temperature and the number density that you want and the exposure time. So for a particular reaction to take place and your interest actually. If you are doing with some material, then you are not much bothered about the temperature, gas temperature, because they can bear. But if you are going to work with living cells, then you must keep in mind the kind of temperature you are handling in these devices. Okay. So now what I would like to tell you that uh, two interesting two interesting applications of this device and how they are able to impart their effect. One thing I have told, this is the H2O2 generation. So when you are discharging this plasma, this APPJ jet on water, as I told you that they will be generating the OH radical, because of the natural vapor pressure of the water. Some of the particles are getting evaporated at the interface between the plasma and the liquid, and there they are breaking these OH molecules and forming OH radicals. Then OH radicals are combining and they are forming the H2O2. So not only that, they break oxygen and then produce nascent atoms. This nascent oxygen atom join with oxygen molecule and form ozone. So ozone generation is also a part of this device. Then you are seeing the H2O2 concentration as you keep on applying the jet over water for time. These are in seconds. So this is 10 minutes over here. So you are discharging and you see that the concentration is increasing very efficiently. But of course it cannot increase indefinitely. After certain time it must reach a plateau region. So that part is not investigated here. It is up to this seconds. So the we have seen that the concentration of H2O2 increasing. So H2O2, that acts as antimicrobial agency for sterilization purpose. So this can be used directly for this sterilization application. Then what other things you are getting, that you see that it is breaking the nitrogen atom in the air, or if you are pushing nitrogen itself through the plasma, then it is breaking the nitrogen molecule. Now one thing you may be knowing or not knowing, I just want to emphasize that nitrogen is having triple bond. So that is a very strong bond to break. Only the plasma can break it. Even though there is a non-thermal plasma and it is a pulsed kind of plasma that is getting generated, the moment where the breakdown is taking place, maybe locally, they are able to break the nitrogen molecule and from the nitrogen atom, and they are reacting with the oxygen present there and forming this NO2 and NO3. The concentration we have measured using in plasma, and these are in minutes, this was in second. You are seeing that the concentration is gradually increasing. So this is 10 minute, 20 minute, 30 minute, and your nitrate and nitrate concentrations are increasing like this. So these are very small tiny device for localized application, and we are seeing that they can very efficiently produce radicals which can interact and produce other compounds, as we are seeing over here. So these are just showing some of the potential application areas of these atmospheric pressure plasma jets. Maybe it is in kilohertz range, or maybe it is in RF range, which we have just described. So that are the things which are very important as these devices are now emerging in the plasma application areas. Now I will be coming to another very important device which are being studied in the field for quite long time. So they are called atmospheric pressure plasma jets, but based on the DVD discharges. DVD means your dielectric barrier discharge. Okay. So in this device, what you are seeing a schematic of the configuration and what are the essential elements in that. So this is a gas tube, usually glass tube. Glass may be quartz, or even you can use ordinary glass also, because the temperature is not high. Gas temperature is never high, so you can use that as well. Now what we have done, there is a central electrode is placed along the axis of this tube, and outside that, what is this? This is a glass tube. Okay. And the glass tube is wrapped using a copper foil. in this zone only. So you take a copper foil of that width and then wrap it over there. So this copper foil is conducting. So you connect that to some through some wire, and you connect with the central electrode via a power source. Again, the power source whatever you are using, it should be able to provide very high voltage, although in a pulsed manner. So what is the difference between the direct discharge, where there is no dielectric between the outer electrode and the central electrode, and this one where we have put a dielectric media like the glass here between the central electrode and the outer electrode. So you are seeing here several interesting things compared to the one where we did direct discharge. So what are the special effects what you are seeing here? The first one is residual charge species. Afterglow particles like electrons, ions and metastables can persist for milliseconds or longer, influencing the next ignition. So this is something called memory effect. Okay. So this electrons, ions and metastables can persist for milliseconds or higher, which can influence the next ignition because it is in pulse mode. So this pulse has been applied and these are generated, electrons, ions and metastables. How they are influencing? Because there is a dielectric and it can charge the dielectric or it can sit over there. So when this charged particle is sitting on some dielectric surface, they are producing their own field and they are changing the surface behavior. So that way they are now helping, rather they are now influencing the next ignition, which of course depends on the electric field and the surface condition. Now surface absorption and desorption, how that happens? Active species can absorb onto surface like electrodes or substrates and later dissolve. So they can come out from that surface. So they are contributing additionally when you are making the next pulse, when you are applying the next pulse, these dissolved your active species are coming into the plasma and influencing the plasma. And you are now thinking probably that what percent of that will get dissolved or absorbed in the on the surface. So actually the number density what we are talking about is in the range of 10 to the power say 19, 20 kind of thing. So part of that even if get dissolved or absorbed, then they have potential to influence the discharge in a significant way, and these are practically seen in such devices. And what are these? They are thermal effects. Heating is happening whenever you are causing the discharge. Maybe it is small, maybe it is momentary, but heat is getting generated over there, and they are heat retained in the gas or surrounding material like your dielectric or mainly or the electrodes. If the heat retained in the gas or surrounding material, they can reduce the breakdown voltage or modify the flow pattern, especially when you are having two electrodes. One is having absorbed active species in them and a modified surface area because of the ion bombardment or some such kind of thing, then that they have potential to influence the next discharge. They can lower the breakdown voltage because of the sharp edges, sharp electric fields are getting created over there in the sharp edges. So those electric field can influence the next discharge, and the surface condition, whether the desorption will take place or not, that very much depends on the thermal scenario. So that can cause break down at a reduced voltage while the discharge take place. Then wall conditioning. So previous discharges can chemically or physically alter the dielectric walls or electrodes. So changing the discharge characteristics over time. So now you are seeing that it is pulse after pulse. So in one pulse some absorption has taken place and some desorption has also taken place before the next pulse. But if there is residual charge there, then pulse after pulse it may happen that residual charge will increase and they will actively influence the discharge event in a very significant manner. So what you need to do, you need to take care of all these effects while you are actually considering a DVD discharge. So now what I will do actually, I will start discussing about another very important plasma device, which is ECR plasma source. ECR stand for electron cyclotron resonance. Now ECR plasma sources are basically used for surface treatment where you require a very pure kind of plasma and you want to generate multiply charged ions. So those multiply charged ions are of substantial importance when you are going to accelerate. So suppose you are applying some field and your atom that you want to accelerate is singly charged. So the force, if the charge is E, then the force that is applied is E into E. So small e is the electric charge and the next E is capital E, that is the electric field. The moment you are able to make it doubly ionized, then the force that you are applying on the atom becomes doubled, that is twice E into E. So now the force is doubled, so you can accelerate it much faster. So this type of ECR plasma source are often used in ion accelerators. So I stop here in this class, and in the next class what I will be doing, I will be discussing more on the ECR plasma sources, which is a very significant development in the area, and still research are going on to make this device more perfect. So I stop here, I will meet you in the next class.